Electromagnetic waves. This is a little bit going to be a little bit different than the way that the book treats electromagnetic waves. First thing I want to talk about is the very various ways in which wave equations show up. Hopefully, you've all done, your undergraduate electromagnetism class, so you know that there's this wave equation for the electric field and a magnetic field. But hopefully, you also remember that there's this set of retarded potentials that we discovered a couple of weeks ago, where we have basically a wave equation for the vector potential on the left-hand side and some kind of a source term, let's say a current, on the right-hand side, and something similar for the electric field. So some kind of a wave equation for the electric field, for the electric potential, and then some kind of a source term on the right-hand side, which has the charge density. So that type of equation shows up a lot. And when we solve differential equations, oftentimes, we kind of limit ourselves to solving it only for one particular type of field. But really, hopefully, you'll agree with me that once you have done it for one type of field, or scalar field, vector field, you've done it for all fields. So what I want to do today is show you how the most general solution for this type of wave equation proceeds. And of course, it does that with our friend, the Fourier transform, because we know that Fourier transforms convert differential equation problems into algebra problems, right? So instead of having first, second, and zeroth derivatives, you end up with a polynomial. So it's much easier to write the solutions. And then we'll use the fact that we have this very powerful way of showing how a derivative and a cross product and a dot product and a curl and a divergence transform under a Fourier transform, and we'll be able to show very straightforwardly that electromagnetic waves have to be transverse electromagnetic waves, and it comes all from this very high level, Fourier transforms and our partial derivatives becoming I omegas or I k's. So we'll do that first. And then I want to talk about radiation pressure. Radiation pressure is that thing that people have been talking about for a long time, is to harvest, to harness that to propel big sails, like solar sails, basically, in space. Because the nice thing is radiation pressure is not you don't have to carry your own source of fuel, and that radiation pressure keeps being exerted on some kind of a sail. And even though the pressure is low, let's say here on Earth, I think it's micropascals. So the pressure is low, but it is not zero, and it is free forever. So in the end, you might still come out ahead because you don't need to carry your own fuel. So it's super useful thing. But I want to use the Maxwell stress tensor to get to the radiation pressure because it allows us to also very quickly see what happens if, instead of having some kind of object that absorbs waves versus when it reflects waves, it's very easy to see where the factor 2 comes from. Of course, it comes from momentum reversal versus momentum absorption. But when we do this with the Maxwell stress tensor, you have a bit of a different angle to it. So we'll do that last. So let's talk about electromagnetic waves. So we have already done our derivation. We know that the sourceless wave equations are very easy. Sourceless Maxwell's equations. Sorry, Maxwell's equations lead to the sourceless wave equations. And of course, we have our wave equation for E. And it's 0. And of course, we can also write this as the D'Alembert of E being 0. And similarly, del T squared of B and then in the Lorentz gauge, so remember no T here. In the Lorentz gauge, we can write a wave equation for the vector potentials like this. Oops. Okay. And the Lorentz gauge, remember, was that divergence of A del T of phi. And then in the Coulomb gauge, it looks a little different. So we still have this, oops, this D'Alembert of A being 0, but the Coulomb gauge is that the divergence of A is 0. And then you end up with Laplacian of phi being 0. So it looks a little bit different. But the advantage of doing the Coulomb gauge is that you only need to solve the equation for A. So only solve, oops, the wave equation for A, and then E and B follow automatically. Okay, so remember that E is minus the gradient of phi minus 1 over C del T of A, and B is the curl of A. And usually, we can just assume that if the Laplacian of phi is 0, then in free space, phi is 0 as well. So therefore, we can just throw this away. Okay, so the Coulomb gauge is also called the transverse gauge. So in the Coulomb, aka transverse gauge, it's easy to show that A is perpendicular to K. Okay, how do we do that? Well, the gauge condition is that the divergence of A is 0. So now if we take the Fourier transform of both sides, I'll just take a Fourier transform both sides. So we take a Fourier transform of the, oops. Transform 0. Okay, this now taking the gradient, you can pull it out of the Fourier transform or the divergence. We can just swap it out for an IK. So we get IK vector. And then we can pull it out of the Fourier transform. So what we have left here is the Fourier transform of that original function. And then on the right-hand side here is 0, because the Fourier transform is a linear operator. So if the Fourier transform is, so if the thing that you're integrating is 0, then the Fourier transform is also 0. Okay, so this thing we can just write as IK dotted with A. And this is, I'm usually putting a little tilde on top of the A to indicate that we're talking about the Fourier transform. So this is Fourier transform of A. Okay, and now we already have it. So because that dot product of K and A is 0, K is perpendicular to A. Because it's perpendicular to the Fourier transform, it's also perpendicular to the real thing. Okay. Now, I want to talk about what 0 means for a little bit, if you'll indulge me. Okay. So, what do we mean by and 0? Okay, so when we write something as 0 or something has these 3 stripes. So let's talk about that a little bit. So let's say we have some kind of a function. And this is x. And let's say this function is, some kind of a cosine. So some kind of a cosine of kx. And we have another function, some kind of function g, which is, it's actually just 0 everywhere. Okay, so this one is a sine wave or a cosine wave, and the other one is always 0. Okay. If you look at f, you see that here, f x is equal to 0, but it only happens in very specific spots. Here, we have g of x is 0, but it's not just 0 in particular spots, it is 0 everywhere, identically 0. So this 3 lines of the definition thing, they're used in many, many ways. So in LaTeX, it's equiv. So that's an easy way to read it. So when you say something is equivalent, that means you could swap it out. It's not just that it holds for a special case. You could just swap it out. You can also read this as by definition, or always. Okay, and this is then, I guess, sometimes. Oops. Okay, so this comes back to our Fourier transform. So let's say, let's calculate the Fourier transform of f and g. Okay, so Fourier transform of f, well, it's like this. So f of x, e minus I kx dx. Okay, the cosine of x we can write as e ix times k. We should use a k prime here. Okay, ikx minus e minus I kx e I k prime x dx. Okay, we're integrating from infinity to infinity. Okay, hopefully you'll get two terms here. You'll get an integral with an e I x k minus k prime dx minus an integral ix k plus, sorry, this is plus, and this is k minus k prime. Yeah, I think I did that right. Let me make sure that I get my signs right. Yeah, so I think I did that right. So hopefully you'll recognize this as this is a delta function of k plus k prime, and this is a delta function of k minus k prime. Okay, so you'll get two peaks, one at k plus k prime and one at k minus k prime, because the Fourier transform has two peaks. Okay, so let's do the same thing for G. And this is easy. G, okay, minus I kx. Okay, so I'm going to pull my G out because G does not in fact depend on x. So it's just e I kx dx. Okay, and because G is 0, this thing is 0 times whatever is on the right hand side. So in the context of Fourier transforms, it is important when we say something is 0 that we're saying, is it 0 for a special case, which could be the case for like a cosine type wave. And then when you take a Fourier transform, you get delta functions because there's definitely something there. It's not 0, or something where it is identically 0. And then we need to pay attention to that third equal sign. Now, what are the general properties of solutions to a wave equation? All right, so we have the D'Alembert acting on something is 0, or minus 1 over c squared del squared t of something is 0. This is the structure that all of them have. Okay, so now we invoke our Fourier transform, but now we're going to use the Fourier transform for both k and omega. So we're going to take the Fourier transform for both k and omega of this thing, this entire thing. And now on the right hand side, because this thing is identically 0, the Fourier transform is also 0. Okay, so really we don't do this, but we really could write a third line there because it is 0 everywhere, because the wave equation doesn't allow for anything on the right hand side unless you have a source term. Okay, so the Fourier transform of this thing, let's do it. So Nabla operator becomes ik vector, so this becomes ik vector, and squared, or in other words, dotted with itself. And then it's still operating on, it's multiplying this Fourier transform of whatever the thing is that we're taking the transform off. Okay, minus, and then there's a 1 over c squared. And now our del t is going to become an I omega, and I believe there's a minus I omega here. And we square it, but because I can never remember which one has the plus and which one has the minus, this is a thing for your cheat sheet. It's also a little bit of a function of convention. Doesn't really matter. And we're taking the square here anyway, so it's fine. Okay, so hopefully you see here that now that Fourier transform, or whatever that thing is that we have in dots, has some kind of a behavior that we can factor out. So we can say, well, the Fourier transform of that thing times, all right, this is ik squared. And of course, I squared is minus 1, so that becomes minus k squared. Of course, k vector dotted with itself is just k squared, length squared, kind of by definition. Okay, minus 1 over c squared. And this times minus omega squared is equal to 0. Okay, now there are two solutions here. We have, product of two terms. We have the Fourier transform of that thing could be 0, right? So that field could be 0. So if the electric field, for instance, we're solving the wave equation for the electric field, let's say the electric field is 0 everywhere, it satisfies the wave equation. It's just not a super interesting thing, because even though it satisfies the wave equation, it is not actually carrying any meaning. So that's what we usually call the trivial solution. That's what we usually call the trivial solution. And then finally, we have that other thing, or we have our k squared, and we have a minus, so we're going to do omega squared over c squared minus k squared is equal to 0. Okay, so in other words, omega squared is c squared k squared, or omega is plus or minus ck. Now, this is the dispersion relation. And of course, we have many different ways of writing this. We know that, versus we could write this as 2 pi f, and we can write this as plus or minus c times k, but k itself is 2 pi over lambda, right? So you get 2 pi on the right, 2 pi on the left. So we have lambda f is plus or minus c. That's the other way in which oftentimes electromagnetic waves are characterized. Now, hopefully you agree with me, is that this is kind of cool that we get this relation between the speed, the wave number or the wavelength, and the frequency, or the angular frequency, or the period, that is independent of the field that we were considering, right? This is just anything that looks like this wave equation. So we said Laplacian squared minus 1 over c squared del t squared. Anything that satisfies that wave equation must have this relation between the spatial part and the temporal part, and those are related through the speed of light, c. So this holds for any kind of wave equation that satisfies this thing. So find it useful to do that. All right, now let's do a little exercise. Okay. Use Faraday's law to show that B is perpendicular to K, but also E. So by now, hopefully, you are developing this Pavlovian response. We're going to use the Fourier transform. Okay, so we start with Faraday's law. So Faraday's law in differential form is this minus 1 over C del T of B. Okay, now we're going to take the Fourier transform of this thing, and then also the Fourier transform of this thing. And this is the, again, this is the 4D, aka spatio temporal Fourier transform. All right, so we pick up an IK vector, and here we end up with the Fourier transform of E. And on the right-hand side, we pick up a minus I omega. So we get a minus 1 over C times, times minus I omega. And then we are left with the Fourier transform of B, which let's just write it in one go. The Fourier transform of B. Now, throw these away. Okay, now we have here also the I. Okay, there we go. So K cross E is omega over C B. All right, now cross products. A property of the cross product is if you take two vectors and you take a cross product, as long as these vectors are not pointing in the same direction, the vector that comes out of a cross product is going to be perpendicular to both the first, the left thing on the left side of the cross product and the vector on the right hand side of the cross product. So we know that by definition, really, let's do this in black like a person. Okay, by definition, we know that B is going to be perpendicular to K, and B is perpendicular to E. Okay, now that's in the reciprocal space. Okay, now we just need to translate this to real space. Like, are we allowed to remove those tildes over those fields and this thing would still be true? Well, we are, because when we say that, let's say, B is perpendicular to E, what we really mean is that B dotted with E is identically zero. Okay, and because it's identically zero, when we take a Fourier transform, it's still going to be zero. So that means that also B dot E is identically zero. Okay, and the same thing here. B is also perpendicular to K. Okay, done. Easy peasy. Now we can do the same thing for the reverse. We can say, and actually, let's write this a little bit more compact. Okay, so we have here, because we'll need it later, K cross E is omega over C B. Okay, now Ampere Maxwell. Do the same thing. Curl of B is 1 over C del T of E. Okay, so this becomes I K vector crossed with B Fourier transform, and this becomes minus I omega over C E, like this. Okay, and we can drop our I's. Okay, so we have here different equation. We have a K crossed with B is omega over C with a minus sign in front. Okay, so similarly here, because this is a cross product, the incoming vectors K and B form some kind of a plane, and the vector that's perpendicular to that plane, that's going to be E. And because it's perpendicular to that plane, it's going to be perpendicular to both the vectors that constitute that plane. So E is going to be perpendicular to K, and E is also perpendicular to B. Okay, so E perpendicular to K, and it's perpendicular to B. Okay, so in other words, E, K, and B form a nice perpendicular set of vectors. Now, hopefully you know this, that E and B, because they are these fields that show up in electromagnetic waves, and we know that electromagnetic waves are transverse waves. Now we see that follows straight from the Maxwell's equations. All we did is we used those cross products and the magic of the Fourier transform to show that those things are perpendicular. So this is consistent with what we know about EM waves being transverse in nature. Okay. Now, let's talk about the flow of energy. So, Poynting vector. All right, so the Poynting vector, of course, we know, S, it's C 4 pi E cross B. And we can just simply take the Fourier transform of all of these. Okay. Now, when we have S here on the left-hand side, and we have an E and a B on the right-hand side, we have now two ways to translate E into B and B into E. So for instance, we have this, let me see, where's my expression here? The red expression here, K cross E, is omega over C B. So in other words, we could substitute our B with this expression in red, or we could do the same thing with the blue expression. We could plug in our expression for E and then get something in terms of B. We'll do both. Okay, so here we go. So the red expression, K cross E omega over CB. Okay, here we go. K cross E is omega over CB. Okay, so let's bring the C over omega to the other side. Okay. And then let's also remember that omega is CK. So really, this is K unit vector cross E. Let's do this with tildes is B. Okay. So into Poynting's vector it goes. So continuing, we have a C over 4 pi E cross B. B, and now here we put B being K cross with E. And I forgot a little tilde here. Okay, now we'll do one of these triple product rules. Okay, so we have C over 4 pi, and then we get E cross E times K minus E dotted with K times E. Okay, now this here is a 0 because E and K are perpendicular to each other. Okay, so this is simply C K vector over 4 pi E squared. Okay, now remember that E squared is a scalar, so this expression is valid and legit. Okay. Now, the blue expression, so S is C over 4 pi E crossed with B. Now we're going to take the blue expression, so K cross B is minus omega over C E. K crossed B is minus omega over C crossed with E. Okay, let's bring our C over to this side. So that's C over omega. Okay, so this is again K unit vector crossed with B. It's minus E. Okay, so we can plug this in. We get C over 4 pi E. Okay, so this becomes minus K crossed with B crossed with B. Okay. Okay, so let's do some work. That's C over 4 pi. And we could do the same thing as we did before. And we'll find this times K vector. Here's another one of those triple product rules. Now, check this out. We now have two expressions for the pointing vector. We have this red expression that came from our substituting B and get an expression for E only. And we have this, well, actually, let's be consistent. Let's make this blue. We have this expression, which is the result of substituting the blue substitution. And of course, because it is the same pointing vector, these things should be identical. Okay, because the power carried by an electromagnetic wave doesn't really matter on whether you write it in terms of E or B. But you'll notice, hopefully, that the expressions are identical, right? The only thing that's different is that E squared or can be swapped out for B squared. Okay, so what do we find? We find that E squared is equal to B squared. Okay, that is a property of electromagnetic waves that is unique to CGS. It is not the same in SI units. In SI units, you need a C. The B is usually smaller by a C in the SI unit system. So only in CGS. In SI, E is CB. All right. Okay, now, finally, let's talk about one particular type of wave. So let's calculate the Maxwell stress tensor for a plane wave traveling in the plus z direction. Okay, so we know that for such a wave, we can just write this as some kind of an E naught x hat cosine omega t minus k z. And we know that the same thing can be done for this one. So we have some kind of a B naught cosine minus t. Okay, and remember that the Maxwell stress tensor is like this. It's 1/4 pi. Then there's a 1/2 e squared plus b squared delta I j minus ei ej minus bi bj. We know that the magnetic field has only a y component. So when we do txx, we don't have a b component, so we just have 1/4 pi 1/2 e squared plus b squared delta I j minus e x squared. And of course, this is ex squared, and b squared is by squared. But by the property of this being an electromagnetic wave, this thing is actually ex squared, right? Because the amplitudes are the same. So the grand total, what do we end up with? How many ex squareds? Well, exactly 0. Because this thing is x, which is 1. So ex squared plus by squared is the same as 2 times ex squared, and then divide that by 2, and then subtract ex squared, so it's 0. So txx is 0. And that's interesting. There we go, tyy. All right, we do the same thing. We have 1/2. This is again ex squared, and now this is by squared. This is delta yy, so that's 1. Okay, now the e component is 0, and the only thing we have here is by squared. Okay, but now, again, by virtue of this being an electromagnetic wave, this thing is actually by squared. So this thing, again, is 0. Okay, so in the Maxwell stress tensor, the x and the y components are both 0. All right, so let's look at TZZ. All right, TZZ, 1/4 pi. Okay, here we go. This is 1/2. And now this is going to be ex squared plus by squared. And this is delta ZZ, which is 1. Okay, and it has no ex or by terms here because this is the ZZ component. Okay, so this thing is simply e squared plus b squared over 8 pi. Okay, so that is the only non-zero part of the Maxwell stress tensor. So that's TZZ for an electromagnetic wave that travels in the z direction. Obviously, if this were a wave that would travel in the x direction, this would be the Maxwell stress tensor XX component. That will be e squared plus b squared over 8 pi. Let's say we have that wave. So we have some kind of a wave. And let's say we call this the z direction. We have an E field. Actually, might as well use different colors. Okay, let's say we do this. and then make this the B field. And now here we put a plane. And here E and B is 0. Okay, so what are we going to do? We're going to take a Gaussian box and we're going to put it here. So I'll make this Gaussian box look like this. Okay, so that's the box, and we're going to put it over there. And we know on this side, T is not 0, and here on this side, T is 0. Okay, so now the Maxwell stress tensor comes into play as follows. So we have this force in the I direction. It's minus that integral of the stress tensor Tij, where we look at the D2Sj normal. Okay, so the only thing that we pay attention to is the Z component. Okay, because it's the only one that has non-zero entries. So if we put this in this box, we're going to get minus T ZZ times the surface area of the box times minus Z. Okay, because the normal, where the tensor is not normal, is the normal that's pointing in the direction that is opposite to the Z hat direction. All right, so this box, it only sees a flux through this face. Because when you put this box on that green plane, it's only the left face that sees a finite stress tensor. The face on the right doesn't see anything. So the normal to that yellow plane that I just colored is pointing to the left. So that's the minus Z hat direction. So those two minuses, they cancel. Okay. So in other words, we get a pressure, which is just going to be T ZZ over the surface area. And TZZ we know because it's this expression, it's E squared plus B squared over 8 pi. Now, important thing, this is a pressure. It is, the pressure is pointing in the plus Z direction. And in fact, TZZ is always positive or 0. It is never negative, right? Because E and B, they will oscillate as a function of time, and they will move as things through space. So there will be moments when this pressure is 0, but it will never be negative. So this pressure is going to basically wobble back and forth, but it will always be pointing in the Z direction. Okay, so this is what we call radiation pressure. Now, I want you to look very carefully at this expression here, the way we got this stress tensor. Notice that if this were a wave that would be traveling not in the plus Z direction, would be traveling in the minus Z direction, the E and the B field might have a different relation, right? They might, because E cross B gives you K, right? So if K is in the different direction and E and B are forming a different kind of a right-handed pair. But those numbers, because we square them, will not change. So in other words, this stress tensor is the same independent of the direction in which this wave is traveling. Now that's crazy. Think about that. This wave, if it is incident on this green plane, that stress tensor on the left-hand side looks the same if that were a wave that would not be traveling towards the plane, but it would be traveling away from the plane. It'd be the identical stress tensor. What does that mean? Well, it means that if you have a reflected wave, you get double the pressure because now you have a TZC for the incoming wave, that is some kind of a number, and you have a TZC for the outgoing wave, and it's identical, it's the same number, or some kind of a time average number if you want to do it this way. Or think about it this way. Let's say our green plane is not a thing that's reflecting, it's reflecting a wave. Let's say this is the source of a wave. Let's say this is a laser, right? Let's say you have a laser, you have some kind of cavity, and you have an electromagnetic wave that points to the left. The stress tensor on the left-hand side is going to be something that's non-zero, whereas the stress tensor on the right-hand side, where the laser diode sits, is going to be zero. Which means that when you turn on your laser in space, you'll start slowly accelerating in a direction opposite to the way that the light is traveling, because you're giving momentum to the electromagnetic wave. And because the wave is traveling away from you, that momentum pushes you away from the way that the wave is traveling. So that's the beautiful thing about thinking these kind of situations through in terms of the Maxwell stress tensor, because it doesn't really matter how you got the E and the B field to do what it is. These could be E or B fields that come from nowhere and are incident on a plane and absorbed, or these could be E and B field that are reflected, or it could be something that you are yourself sourcing by turning on a laser or some kind of an incandescent bulb. Doesn't matter how you do it. If you do have a gradient where you have a tensor that is stress tensor that is non-zero on one side and it's zero on the other side, there will be pressure. That's it. Most general way of saying it. And that's why, like I've been saying, preaching to the choir, I hope now, Maxwell stress tensors are such a useful concept. And of course, a note added in post, as they say, is that of course, if you took your force and you divide it by the surface area, you get the pressure. So that's better.